Mark,
Yes, sir.
can you hear me?
I sure can.
All right, sir. So I think we're all set, and please go ahead.
All right. So hello everyone. My name is Mark Grover, and I'm here to talk about an introduction to Apache Hive and HCatalog. And I'm also going to do a demo at the end of this presentation. The code and the Hive queries that I used for the demo are on my GitHub profile, so you can find them at the URL that I listed there. Before I get started, let me talk a little bit about myself. I am a contributor to the Apache Hive project. Apache Hive, as you know, is an open source project. I've also written a section in O'Reilly's book on Hive. The book is called Programming Hive. I work as a software developer on Cloudera, and those are various different means you can get in touch with me over social media. We are going to have a Q&A session at the end of the presentation. So if you have any questions, feel free to ask them. Mehul has been very graciously offering to be my eyes in the room. So Mehul, if you could please raise your hand and show people who you are. So grab Mehul's attention whenever you have your question, and he will somehow magically send that over to me. All right, so let's get started. This presentation is going to cover all these topics. So first of all, I will tell you what Hive is, why you should care about Hive, some features of Hive. We'll go through some architecture details of Hive. We'll talk about a particular sub-project of Hive that's called HCatalog and why it's important and of interest to the community. And at the end, there will be a demo. All right, so this, as you have already figured out, is a remote talk. My apologies for not being there in person, and thank you for taking the time to come out and listen to me. It is meant for an audience who has heard about Hive, maybe have played a little, but not a whole lot with Hive, or who has just, played around with other parts of the Hadoop ecosystem and have always wondered what this Hive thing is all about. So there aren't a whole lot of assumptions that I make in my presentations, except the fact that you are vaguely familiar with Hadoop and what benefits it brings to your organization. With that said, if you have already played with Hive, we are going to go through some architectural details that may still interest you, so I hope you find something interesting there. And like I said before, ask questions anytime, and grab Mehul's attention if you want to do so. All right, so we move on and talk about what Hive is. So Hive is a data warehouse system for Hadoop. That means that while you're familiar with Hadoop, you deployed Hadoop in your organization, or you're convinced about the benefits of Hadoop, but you aren't really in a mood to write MapReduce jobs, right? MapReduce jobs are kind of like an assembly language for Hadoop, and it takes a lot of effort, and you need a higher level of abstraction. You need an abstraction that looks like a data warehouse system. Traditional data warehouse systems have been Teradatas and Netezas, and you want something that fits in the Hadoop ecosystem but is equivalent to a data warehouse system. And that's the goal for Hive, right? It enables you to do ETL operations. ETL stands for extract, transform, load, right? These are operations that are typically done in and around data warehouse systems historically. So extract could be, let's say you run an online retail company, right? You've got this website where people come and buy things. And if you want to look back at your month's revenue and you want to look at the web clicks that happened on the website during the past month, you need to do some analytics on that data, right? So in that context, the ETL functionality would be, the extract part would be you taking the Apache server logs from your web server and putting them onto Hadoop or Hive. That would be the extract part. The transform part usually means that, well, sometimes the data needs to be transformed from one space to the other, right? You need to add some extra columns. Maybe you want to add some auxiliary information like which marketing channel did this click come from, right? Was it a direct click on the website, or did it actually come from a Google search? Was that Google search paid, or was it unpaid? Anyway, so you can add this auxiliary information to your data. That's the transformation step. And the last step is the load step, right, where you actually go and load this data into a warehouse so people can query it. And then you could be sitting at the other end of this warehouse trying to figure out, well, how many people came to my website last month, and how many of those people were from New York City, and how much did they purchase on average, right? So ETL functionality is what Hive allows you to do in the Hadoop ecosystem. Another important part of Hive is called the Hive Metastore. So what the Metastore does is it allows you to work at a table abstraction, right? So up till now, when we talk about putting data in Hadoop, we talk about data that's just raw, right? So it could be text files, it could be images, it could be Avro files, it could be sequence files, it could be columnar formats. So you can put your data in Hadoop in any format you like. But many people, when they like to query this data, they want to have a higher level of abstraction. They want to have a table level of abstraction. They want to say select star from my table will give me all the records. Or if I want to see how many people bought stuff on my website last month, I would say, you know, select sum of purchase column from my web data where month is equal to last month, right? So in order to have that table abstraction, Hive provides a service called Hive Metastore, which will map a logical table, so the table that you see as web clicks, to a physical location on HDFS, right? So it will say that the data that corresponds to this table lives in a particular location on HDFS. So there's a mapping there, and that the data that is related to a particular table will be serialized and deserialized based on a particular set of library, right? And the reason I say that is because raw data needs to be transformed into a set of columns, right? So your data could be present in the form of a JSON. It needs to be transformed to a set of columns, a set of records. And Hive allows you to do that by having this service called Hive Metastore. We'll talk more about that. Hive can also read, obviously, data from HDFS, but it also has storage handlers for reading data off of HBase and MongoDB. And query execution is in MapReduce. The benefit of this is that MapReduce on its own is fault tolerant, it's scalable, it's robust. So because Hive builds on top of MapReduce, it gains the benefit that comes with MapReduce and HDFS, right? So it is linearly scalable, it is fault tolerant, and it is robust. All right. So now we move on to why we care about Hive, right? You can obviously deploy a Hadoop cluster and run MapReduce jobs. I mean, you would be fine. No one would ever complain about it. Anything you ever wanted to do should be possible in MapReduce job. But why Hive, right? And the answer is MapReduce is catered towards developers, right? You need to be a Java developer, or if you're using Hadoop streaming, you need to be some sort of developer to be able to write a MapReduce job. And Hive, as I mentioned before, provides a higher level of abstraction. There is a whole community of analysts that know how to write SQL very well. These are the guys who will crunch our data and tell us what the website needs to improve, or how we can improve the bounce rate, or how we should invest our marketing revenue, right? These are also the people who will write SQL queries to sequence genomes, right? All these people are particularly good at SQL. They aren't necessarily good at being Java developers or software developers in general. And when Hadoop came up, it presented this platform to store massive amounts of data, but it kind of alienated this community of analysts and people who were SQL savvy from being able to use that data, because the only paradigm you could use to query this data was MapReduce, right? So Hive bridges that exact gap. It says, well, you want the power of Hadoop, you want to store your data in Hadoop, you like Hadoop, but you want to write SQL queries at a higher level abstraction. That's why we present to you Hive, right? So moving on to the third point there, the data in Hadoop is generally unstructured. And this is one of the benefits of Hadoop, right? If you think about one of the things that Hadoop people get very excited about, it's that your data doesn't need to have any structure when you put in it. and it's really good for unstructured and semi-structured data. So what does that mean, right? In historical relational databases, what you do is when you persist the data into a database, you have already thought of the schema of the thing, right? You create a table and then you insert data into it. Oftentimes, I'm going to carry on with the web analytics analogy. If you are collecting Apache logs, there are only a certain subset of information from those logs that you care about today, right? You may care about the IP address, the time the click happened. You may care about which operating system the click came from. You might necessarily not care about what the cookie of the user was, or what some other parameters in there were, or what browser it came from. So because storage in traditional relational databases is expensive, you oftentimes you get rid of this information in the transform phase of the ETL process, and then you store it down in your database, right? What you have done implicitly here is you have thought about the structure that you're going to put on the data when you persist the data, right? This is called schema on write. You have thought about the structure you're going to put on the data when you persist the data. When you read the data, you are stuck with that schema. Now, one of the benefits of Hadoop is that it's schema on read, right? All you do is you dump the data in Hadoop, in HDFS, in the raw ProRest form, because you want to keep the options open to analyze it in whichever waveform you want down the road, right? And that's one of the benefits of Hadoop. So Hive preserves that schema on read methodology. Even though you do apply schemas, even though you call certain things tables, you can apply as many number of schemas on a particular data set to query that data set. So you as a BI analyst could be using a different schema on the same data set, while someone else as the CFO of the company might be using a different schema on the same data set, right? So just because you are applying a schema and Hive allows you to apply a schema doesn't mean that we are deciding that schema at right time, and I think that's an important distinction. And like I said before, you love Hadoop already, you want a high level abstraction, and because Hive is built on top of MapReduce, it is fault tolerant, it is robust, it is scalable. All right, so let's move on and talk about a few Hive features. Just like you would expect from a regular traditional database system, Hive will provide you most of the regular features that come in a database. You can create tables, you can create views, you can create indices, you can write select queries, where clauses, group bys, order bys, joins. Hive also has an added emphasis on pluggability. So if you think about MySQL, you've got these two functions, from Unix time and Unix timestamp, right? These functions, from Unix time takes a Unix timestamp and converts it into a human readable form, and Unix timestamp does the vice versa. Now, in today's world, you can envision cases where you want to write functions like that, but those are custom logic. You don't want them to be outside of the company. People outside the company or organization, or people apart from you, might not have envisioned the same functions, right? And it's really easy to write a function like that in Hive. It's called a UDF. It stands for user-defined function. And you essentially write your own from Unix time, right? Or write your own Unix timestamp, or any function. Essentially, a UDF is a custom written function that will take one record of data and convert it into another record. Hive also allows you to write your own UDAFs. A UDAF is user-defined aggregate functions. Examples of those are like average, count, percentile, similar to UDF, except that they operate on a set of rows instead of just one row at a time. Hive also allows you to write pluggable UDTF. UDTF is a user-defined table generating function. So what does that mean? UDFs operate on one record of data, give you one record. UDAFs operate on multiple records of data, give you one record. UDTFs operate on multiple records of data and give you multiple records, right? So this is the first kind of function that will give you multiple records at the end of the computation. And this is somewhat required. So if you want to, say, take an array and explode it out into individual records, you would use a user-defined table generating functions. Anyways, you can write your own user-defined table generating functions and very easily use it in your Hive queries. Also, we have the option of writing your own input and output format. So your organization or you might have some really fancy format that your data is present in. And Hive, out of the box, comes with support for some formats, right? Like these formats are text files, column delimited files. These are columnar formats like our C file. These are sequence files. But you may have your own format. And again, one of the benefits of Hadoop is you can plug in your own format and just be able to query it. And Hive allows you to, again, do the same thing. You can write your own input format. You will create these two new classes, Hadoop input format and output format, and be able to use them. In order to convert your custom format into a sequence of records, you need to be able to serialize and deserialize that format. Serialize means you take a bunch of records and you persist them in that binary format onto HDFS or a similar system. And deserialize means you essentially take the binary format, the binary files from HDFS, and you deserialize them into some columnar chunks that get read in as records of the table, right? So Hive allows you to write your own pluggable serialization, deserialization libraries. These are called SERDEs for short. And the last point is that you can still write your own custom map and reduce scripts within Hive. The reason this is important is because SQL is a stateless language. So there are certain things inherently that are very hard to express in SQL queries. And if push comes to shove, and I have done this in the past, you can write a Hive query, and in there you can say, by the way, I want this query, this script to be my map script and this script to be my reduce script. So you can still get rid of a lot of boilerplate map reduce code by writing the query in Hive, but for parts of the query that you really cringe and want to be able to write a map reduce jobs, Hive allows you to easily plug in a custom map reduce script for whatever analysis you are trying to do. All right, so it's important to talk about what Hive is not, right? Hive is not an OLTP system. OLTP stands for Online Transactional Processing. The basis of that system is that everything is a transaction that needs to be committed. It's meant to have low latency. It's the kind of system that you would use at the back end of any online retail company, for example, right? And Hive is not that. Like, you cannot expect to insert a row or modify a record and expect a sub-second response. What Hive is closer to is what's called an OLAP system. OLAP is Online Analytical Processing. So an OLAP system is usually the one you would look back and analyze data in bigger chunks, right? You're not dealing with single records at a time. Rather, you're dealing with sets of data, right? You're dealing with a month or a year or whatever partitioning scheme that you want to use, but a collection of records at a time usually. And that's what Hive is good for. Hive also doesn't support correlated subqueries. It's like this SQL feature that will allow you to refer to a variable from the outer query and the inside query. I personally don't think that's a big deal. The reason I say that is because most of the times I have had to write correlated subqueries and said, darn it, it doesn't support it. I have been able to easily write a nested query to be able to do the same job. So I don't think that's a big deal. And like I said before, it's not super performant on small amounts of data, right? Hive is meant to be catered towards a population of people that have a variety of data and a whole huge amount of data. The volume is really big, and it's also the velocity derives that is really huge as well. So it's catering towards large amounts of data in a scalable, robust manner than to be like this very optimized sort of SQL engine that will compete with your best OLTP solutions out there, right? Having said that, Hive is still very performant for what it does, I just would like to reiterate that it's meant for certain use cases, and if you have those use cases, you will be a happy camper. And if not, well, then you should probably look at something else. So that kind of begs the question, right? How much data do you want to call a big data, right? Like, when do I transition from my regular MySQL database to start using Hive, right? And obviously, the answer really depends on the kind of data you have in your particular situation. But the kind of benchmark that I use is that if you have, say, a couple hundred gigs of data that is fairly structured and you don't expect it to grow all that much in the future, it's probably not a good candidate for Hive, right? Like, the data that's a good candidate for Hive is that it doesn't have a good structure. Weblogs are obviously a good example of that. Or if it's huge, right? Like, you have a genome sequencer and you want to, write all the genome sequences in a file and then analyze them. That's there. So if your data is very semi-structured or unstructured, if you have massive amounts of data, and if it increases at a vast pace, Hive's your man, right? I also want to state, so the interface to talk to Hive is obviously a query language that's very similar to SQL. We don't call it SQL, we call it HQL, stands for Hive Query Language. It's essentially very, very SQL-like, right? The reason it's not called SQL is because Hive doesn't conform to a particular standard of SQL, right? So if you ask me today, well, is Hive SQL 92 compliant? Like, no. The answer is no, right? Like, so there are certain things in the SQL 92 spec that, are not implemented in Hive. I don't know if that will change anytime soon, but that hasn't been a requirement from the community. The community, in the end, wants to see products that work and fulfill the function that they're meant to fulfill. So Hive is closest to SQL 92 in my experience, without the support for correlated subqueries, of course. But in general, the language you use to query Hive is HQL, which is, for all practical purposes, SQL, otherwise very close to it. So we're going to talk about certain other Hive features. I'm going to quickly go through them because they probably only interest people who have worked with data warehouse systems before, but I will like to mention them anyway. So there's a feature called partitioning. It's a rudimentary form of indexing. If you think of your data set as being laid out in a directory, you can put chunks of that data set in subdirectories. And the benefit of that is when you're writing queries based on a column and you're filtering out some parts of the data based on a column that was used to create those subdirectories, you can remove subdirectories that you don't need to read the data from. The benefit of this is it reduces the I/O requirement on the query that you're running, and hence makes your query faster. So if you had 10 years worth of data and each year was stored as a separate directory, obviously if you're only querying data for the past year, you don't need to read the rest 9 years worth of data. And so arguably your query would be on, in general with some quirks, about 10 times faster because you're not reading the rest of the data. The way to do that is called partitioning. Sampling is another way to query data. Sampling usually means that you don't query all of your data, but only a subset of the data based on certain parameters and columns, right? So if you have to give a quick answer to your boss about, well, how much rainfall happened in the month of February in New York State, you can provide a probabilistic answer and say this answer has about 5% error. And the way that answer would have been provided would have been through sampling, right? So you're not querying all the data, querying a subset of the data, and based on that subset, you say, well, it may have 5% error. Bucketing is another feature where you physically persist data in different files based on a particular column, by default by using a hash function on that column. The benefit of this feature is that it helps in sampling. It can make your sampling queries faster. It can also make your joins faster. So we wouldn't have time to talk about this in detail in this presentation, but one of the biggest challenges to do on a large scale is joins, right? Because if you have 3 terabyte data sets that you want to join, that's a fairly expensive operation. So whatever we can do to optimize joins, if joins are really important for the community, which they are for many people of the Hive community, would go a long way in making the project better. And bucketing is another way. So bucketing will make your joins faster because it can leverage, you will only have to join buckets with each other instead of joining the entire tables together. Anyways, I'm glossing over some details here. So if you are very interested in how that works, please ask me a question later, and I'd be happy to explain further. Hive also integrates with HBase or other storage handlers like MongoDB. So if you want to use Hive to crunch data on HBase or MongoDB, that's possible. The reason you would do that is because HBase doesn't have a rich SQL interface, right? So you might want the HBase sort of close to ACID properties to read and write data and have the key value stored that HBase provides. But hey, what if you wanted to do like OLAP sort of analysis on that data? And that's exactly where you can integrate with Hive and run those SQL queries, because you can't run SQL on HBase, right? Hive also supports views, unmaterialized views. That means if you want a particular user to see a particular view of the data, then you can create a view and give them access to that view. It's unmaterialized in the sense that Hive doesn't store the data that will be presented as a part when you query the view. Every time you query that view, it will go to the underlying table and run the query that's meant to represent the view. Hive also supports complex data types, so you have arrays, structs, and maps that are supported. All right. So to summarize, it's so far, Hive is a data warehouse system with a whole bunch of features that are very commonly found in regular data warehouse systems. It runs on top of Hadoop, so it has all the benefits of MapReduce in HDFS. Did I miss anything? Yes, it has an added focus on pluggability. So if you have your own custom format or you want to write your own functions or aggregate functions, it's really easy to do so in Hive. Anyway, so we will move on to how you would talk to Hive, how you would connect to Hive. So Hive provides a Hive shell. This is essentially, if you have played around with MySQL, you type MySQL on Bash and it will open up a MySQL client. This is essentially the same thing. It will open up a Hive shell, and you can type your Hive queries, and you will get your answers in the terminal itself. It also provides a JDBC driver, so you can connect through your JDBC application, ODBC driver, same stuff like most databases provide. It also provides a Thrift client. So Hive exposes itself as a Thrift server, and on the other side, you can write a Thrift client that will connect to it. And there are Thrift bindings for Java, Python, and a whole bunch of other languages. For those of you who don't know what Thrift is an RPC framework. So it essentially allows remote processes to talk to each other by serializing and deserializing data from one end to the other. And so essentially, Hive will expose that interface to you, and you can write clients that talk directly over that interface. That's also a very common way to talk to Hive. All right, so let's talk about Hive architecture. At this point, I'm going to show you some fancy pictures. For those who are familiar with Hive, might find those interesting. Those who are not familiar with Hive will obviously get to learn some new stuff. But before we get there, I need to talk to you about a particular component of Hive called Hive Metastore. So why does this particular component deserve a special mention? So we talked about how people want to read their Hadoop data sets with a particular schema in mind, right? I gave the example, if you're a BI analyst, you want to read the data with a particular schema in mind. You're only interested in particular columns that may be, well, the IP address, the geographic region, and so forth. While if you're the CFO of the company, you might have a different outlook towards the same data, and you might only be interested in, I don't know, the number of clicks and how many of those clicks were associated with, let's say, paid Google searches, right? And so what has happened is people continue to use these schemas over and over again. If you're the CFO, you're going to use that schema every single day. And if you're the BI analyst, you're going to use your schema every single day. So it makes sense to persist this schema in a database, right? It makes sense to say that this is the BI analyst's table and this is the CFO's table. Underneath, it's the same data set. Underneath, we use the same serialization, deserialization libraries, but we persist the schema into a database. This database is a relational database. Right now, we support in Hive, we support Derby, MySQL, Postgres, Oracle as well. And I'm sure if you have any other favorite relational database that you want to use as a Metastore, Hive can easily be worked to support that if it doesn't already support that. And the component in Hive that allows you to write the schema to a relational database is called Hive Metastore. Schema in this context usually means, well, what are the columns of this data set? What are the types of those columns? Is this data set partitioned? If so, what column is it partitioned by? Where is this data set located? How do I parse out this data set? Do I use a regex, or is it a CSV file? Is it a tab delimited file? All this information is very structured. It's a small amount of information that's a perfect candidate for a relational database. And that's why, so Hive has this component called the Hive Metastore, which will store the schema associated with your data set. It's the metadata about your data set that gets stored in the Hive Metastore DB. By default, Hive comes with an embedded Derby Metastore. It's essentially a Derby database that runs in the process of Hive. It's not recommended for anything useful. So if you're doing any development or production, move away from embedded Derby. It's only recommended if you're using, you know, a quick evaluation, proof of concept sort of thing. That's when you should use the default Derby. The three modes of operation of Hive Metastore are the default embedded Derby. The second one is local, in which the Metastore service runs in the same JVM as the Hive driver. And the third one is remote, in which it runs in a separate JVM. We'll talk about these in detail shortly. Okay, so let's talk about Hive architecture. So you see this big blob on the top left. That is the Hive crux, right? That's the core of Hive. On top, you have the CLI shell that will interact with the core of Hive. And the core is constituted essentially of three things. There's the Hive driver, then there's the Hive compiler, and the executor, right? Between the driver and the compiler, there's this optional step of optimization. You know, there's a component called Hive Optimizer, which is not shown in this diagram. So the driver essentially takes the query, which is your SQL query, and drives it around to all these components until it's executed. The compiler will take the SQL-like query and compile it into an AST tree. An AST tree is abstract syntax tree. So essentially, it's a tree of operators and operands, an operator being, you know, select or group by or where, and operands being, you know, column names and constants and so on and so forth. So the compiler essentially takes the syntax, compiles it into this tree of operators. This tree of operators can then be optimized to another tree of operators, and that's done by the optimizer. Apologies for not showing that in the picture. And then the executor takes this AST tree and then makes it into a series of MapReduce tasks that get run on your Hadoop cluster, right? Important thing to note here is that your Hive query doesn't necessarily have to map to one MapReduce job, right? One Hive query can map to multiple MapReduce jobs, which get carried out in sequence. There are obviously some queries that only require map phases. They don't require reduce phases. And it really depends on the query you're writing, the data set, and how it's stored on how that query gets compiled into MapReduce. In that big blob on the right, you would see the Metastore component, right? So that's a component in Hive that will talk to this relational database, and it will store the schema, right? So when you say select star from this table, the Metastore component triggers a read from this relational schema to figure out, well, what are the columns of this data set? Where is this data set stored? And passes that information onto the compiler and the executor for compiling and executing the plan. So when I was saying that Hive Metastore can run in a local mode, first, the default mode was Embedded Derby that we are not talking about here. Embedded Derby is different, not useful for most context. We are talking about the second mode here, which is a local mode. So local mode means that the Metastore block is actually present in the same gray box as the CLI shell and the Hive driver compiler and executor. That gray box represents a process. It represents a JVM. So it's in the same JVM. That's one way of operating the Metastore. This is the second way of operating the Metastore. In this case, if you notice, that block that was present in the bigger blob is now outside and to the right. It's its own block, right? And this symbolizes that it's running as a separate process in a separate JVM. So why would you want to do that, right? There are two reasons. The first reason is that this block needs to have the credentials to talk to the relational database, the Metastore DB that you see. If you plug it into the same block as the core of Hive, anybody who's using Hive will get to see those credentials. I mean, the credentials are in a config file, so anyone and everyone has access to those credentials. If you separate this out in a separate blob, you can run the Hive Metastore service on a separate box that no one has access to, and hence your credentials are then secure, and anybody using Hive CLI will talk over Thrift to that block. It will talk over Thrift to the Hive Metastore service that's running remotely on a different box and wouldn't be able to see the DB credentials. So that's one benefit. Second is that there might be other services apart from Hive that want to use that same metadata, right? And for those who are familiar with other parts of the Hadoop ecosystem, there's a project called Pig. Pig is a workflow language, again, a high-level abstraction on top of MapReduce. It will allow you to write MapReduce queries and all that as workflows. And for Pig, it might be interesting to use the table-level abstraction, hence share the same metadata with Hive. And that's why we have the Hive Metastore service running as a separate service. Anyways, so the point is, in the past two slides, I just demonstrated what the architecture of Hive is. If you get to a point where a lot of services are using Hive Metastore, you should consider the remote mode. And if you don't really care, local mode is fine, in which case the Metastore runs in the same JVM. I would recommend against using the Embedded Derby Hive Metastore mode. Moving on. There is this thing called Hive Server, and it's a very confusing name. It's a confusing name because it's a server, but it's not a server that most people like to think of. So let's talk about what Hive Server is first. Hive Server is this Thrift server interface that is exposed on top of the Hive driver, so people can talk to Hive via a JDBC application, right? So it becomes this standalone process that you can talk over JDBC or ODBC or over a Thrift client. The problem, though, is the reason I say this is different than a regular server is because, at least I have thought of servers, when someone says servers, I think of web servers. And web server to me is like, you know, you buy one server and you can entertain hundreds and thousands of connections at the same time. So they are concurrent. Hive server, sadly, is not. So essentially, if you write a JDBC application that you want to connect to Hive, for every client you have, you will have to instantiate a new server. You will have to have a node that's running Hive server. And the reason is Hive server is not concurrent. So even though it's a server, it's a single sort of client-facing server, right? So here are the problems with Hive server. It doesn't have any sessions or concurrency. You essentially need one server per client. It has implications on security and logging, right? And that's exactly why the Hive community came up with this new thing called Hive Server 2. So nothing has changed essentially in the core, right? You still see the driver, compiler, and executor, except that the community has written a new server that's called Hive Server 2. And that server sits on top of these driver, compiler, and executor things. And now you can launch a JDBC client app connected to Hive. It will instantiate or it will pick up actually a worker thread from the pool of threads that Hive Server 2 has. and then instantiate and essentially have a new driver compiler executor chain running that Hive query over Hadoop, right? And if in the meanwhile another JDBC app comes in, connects to the same Hive server, it will pick another worker thread from the thread pool and compile that query and execute it, right? So essentially Hive Server 2 was envisioned because Hive Server 1 was not concurrent. And so the reason I'm telling you this is because if you're just, in the beginning stages of using Hive, Hive Server 1 is just fine, use it. It's obviously been around for a longer time. If you are looking at a deployment of Hive where you're going to have a lot of people connect to Hive at the same time, running queries at the same time to one server, then consider deploying Hive Server 2. Both of these are part of the Hive distribution, so it's just a matter of starting one instead of the other. Keep in mind that the core functionality, the driver, compiler, and executor are still the same. They haven't changed. The only thing that has changed is the top-level interface that exposes the server interface. All right, so I have taken a lot of your time, and I'm going to quickly go through this textual slide. It essentially lists out the features in the compiler. So the compiler will parse your query, it will check your query, analyze your query, generate some plan, generate tasks. Not that interesting, I would say. And execution engine has a plan. It has operators. We talked about operators before. SerDes, these are serialization, deserialization libraries, and they will essentially take your data set from HDFS and present that as a collection of records, and vice versa. When you're writing data, it will take the collection of records and persist them as a binary format. And then you have all these pluggable things that you can plug into Hive. You also have the Metastore, which will store the schema of data. You can store as many schemas as you want on the same data set. All right, so we went through a summary already. Use remote Metastore if you care about sharing the metadata with other things like HCatalog. We'll talk about HCatalog real soon. And use Hive Server 2 if you care about concurrent queries. Otherwise, the status quo is just fine. All right, let's talk about HCatalog. Okay, so this is the same diagram we have seen before, except that I put this red circle around the Metastore service and the Metastore DB. Right, so why would I do that? I would do that because that particular component is useful to other projects. I alluded to this a little bit when I talked about Pig trying to have a table level abstraction for its workflows. Or you writing your own BI app that would like to leverage the tables that you created in Hive. If you say write a Squirrel client for Hive, Squirrel is this interface for accessing databases and writing queries and running those queries. If you wrote a SQL app for your own organization for fun or whatever, you would want to leverage this metadata information that Hive has. And so first, it's important to run it as a service separately. But second, because it has been historically a Hive component, Hive doesn't necessarily do a good job at exposing this information, right? So there was a need for a project to wrap around this Hive Metastore service and make that available to other things in the Hadoop ecosystem. And that thing is called HCatalog. So what is HCatalog? First of all, it's a sub-project of Hive. It started off as a separate project and was in the incubator, Apache incubator, and then it graduated on to become a sub-project of Hive. It's a table and storage management service, essentially a wrapper around the Hive Metastore. And it essentially has these public APIs and a web interface that you can use to access the metadata for tables, right? So if you want to create a Hive table, you can issue this REST put request to create it, right? And if you want to drop a table, you can issue this REST delete request to get rid of that table. And the reason it came into its infancy and matured into what it is today is because Metastore is of interest to other components. If you're writing a MapReduce job, you don't want to write a whole bunch of boilerplate code every time to take this data, figure out where its location is, prune out certain partitions, and serialize that data into something. So using HCatalog input and output formats will allow you to use the Hive Metastore abstraction and convert that data into a set of records that you might just parse directly in your MapReduce, excuse me, in your MapReduce job. So HCatalog also has this server called Web HCat. It's essentially a web server that provides the REST interface for interacting with the Hive Metastore. So here's a pictorial description of the Web HCat. So essentially at the very left there's this user talking over the REST interface to this thing called the Templeton server. And Templeton is actually an old name for Web HCat. I didn't update the image. Essentially you can replace the word Templeton with Web HCat and you would be okay. So you talk to this web server called Web HCat, was previously called Templeton, and it will talk to the Hive Metastore in the background and give you the list of tables as a JSON file and whatever you care about. So that was HCat, right? To summarize, people looked at the importance of Hive Metastore, wanted to share it with other things in the ecosystem, and that's why HCat became what it became. All right, now it's demo time. That was the end of my core presentation. So what I'm going to do is I'm going to open up a demo VM where I have Hive installed. And Mehul, please do me a favor. If this is not big enough, please let me know. Okay, you guys see this?
Yes, it looks good, Mark.
Okay, thank you. All right, so this is some code that I put together for showing a demo. All right, so you probably can't read all of it, but that's okay. I'll explain it to you as we go through. So the data set that I used for this demo is this flight data set. So in the year 2008, because that was the latest I could find, this data set has all the flights that flew from within and into the United States of America, domestic flights. And it has information about which airport it flew from, where it went to, what was the scheduled arrival time, what was the scheduled departure time, what was the actual arrival time, what was the actual departure time. So that way you can do some fancy analytics on this data to figure out, well, in the month of January 2008, should I have preferred to fly from San Francisco International Airport or Oakland Airport, right? And there is another second data set which essentially links the airport codes, so SFO to San Francisco International, and JFK to JFK International, and that's the second data set that I got from like this website. Essentially scraped it off from worldairportcodes.com. Anyway, this is publicly available, so if you want to play around with this when you go back home, that's totally cool. This is a demo VM. So it's a demo VM that Cloudera provides. It essentially is this VM that you download. You can use VirtualBox or VMware or anything of your liking and run it. And it has a whole bunch of Hadoop ecosystem software installed on it, right? So it has Hadoop, it has Hive, it has Impala, and a whole bunch of other things. So I just, for ease of use, I just downloaded a demo VM, and I'm using that for the demo, right? The first thing I did, and I did this before I got here, so I git cloned my repository from GitHub, and that's called NYC Hug Hive. And in here, okay, in here I have a bunch of things. There's a README file that you will see on GitHub. I have the copy of this presentation slides that I used. I have the data set. That's the airports.csv file. You're welcome to look at this. It's essentially the name of the airport, and it's a comma-separated file. So if you want to look at the first row, the name of the airport is Key West, Nad, Boca Fields, whatever, private U.S. Navy airport. The second column in the CSV file is the name of the country, which is U.S. obviously. and the third is the region code, and the fourth is the airport code. So this is the second data set that I scraped off of worldairports.com. The first data set is this tarball, that 2008.tar.gz that I untarred here. So I can open this up. And this is essentially the core data, right? In data warehouse terminology, this would be called the fact table. A fact table is that contains data that happens very frequently. It's like the clicks on your website, or flights in a given month. Dimension data is out-of-band data like user information, or airplane carrier information, or linking of airport codes to full names. That doesn't change all that often. Fact data changes very often. So this is our fact data, and if you want to go through the first row with me here, it says this is 2008 year, the month is January, and I think third column is, we'll look into this, but the third column is the day of the month, which is the 3rd of January. The fourth column is the day of the week, which would be Monday, Tuesday, Wednesday, Friday, Monday, Tuesday, Wednesday, Thursday, geez. So that would be Thursday, I'm guessing. And then next is the departed time, so that's 20:03, 8:03 p.m. Actual departure time, which is 19:55, 7:55 p.m., and so on and so forth. Anyways, so this is some data. Again, when I'm looking at this, right, I have a schema in mind. I know this is a CSV file. I know the first column is this. I know the second column is this. This is exactly the schema that the Metastore stores. So here's what I'm going to do. I'm going to launch Hive, and I'm going to do that by typing Hive on bash. So I get this shell. I'm going to clean this up. And the first command I'm going to do is I'm going to create this table. So I'm going to, for sake of convenience for now, I'm going to copy paste this command from my GitHub profile into the Hive shell. Okay. All right. So I pressed enter after that, and it worked, right? So before we go any further, let's go look at this create table command. So this says create table flight data. For those of you familiar with SQL, it looks very similar to what a regular create table would look like in MySQL or something. The name of the table is flight data, and I say, well, my first column is year, it's integer type, second is month, integer type, day, integer type, day of week, integer type, and so on and so forth, right? It has a whole bunch of columns. At the very bottom, I say it's row format delimited. That means that one record is one row of data, right? It means that one record doesn't span multiple rows. And I also say that fields are terminated by comma, right? It tells Hive that when you parse out this data set, you should delimit fields and split them based on the comma, right? This is essentially the information that will be stored in the Metastore. Anyways, so moving back to Hive, I'm going to do a show tables command, and I'm going to see that there is a flight data table that's there. So right now this table is empty because I haven't loaded any data in there. So next step is to load the data that I got from untarring the tar.gz file that is present on my GitHub profile, right? The way I do that is I run this command. So let me run this command, and then I'll talk about what that command does. All right. Obviously, that command didn't work. Let's see. I'm going to try one more time. All right. It seems like I copied the wrong command, but this time it's working. So this command actually says, load data local in path 2008.csv. So it says pick the file called 2008.csv from my local disk and write it into flight data table of Hive. Now the flight data table by default has a location on HDFS, and essentially we're going to override that location and copy this file from local disk onto HDFS. That's what this command does underneath. And if you notice, this is essentially what happens, right? So it says I deleted user Hive warehouse flight data, and the reason it deleted it because I said overwrite, right? So it first deletes it, and then it loads that file. And at the end, it gives me some stats about what it loaded. It says that there weren't any partitions, excuse me. The number of files there was just one file, and the total size of the data is this many bytes. Anyways, so we still have that table. I'm sure you can see it. If you want to do a select star on that table, and I'm going to do limit 10 because there's just a lot of data, you see the data, right? You see like January 3rd, 2008 has some flight information that might be of interest to us. So now we have done two things. We have created our table, we have loaded the data into this table, and we have verified that the data actually got loaded by doing the select star command. Now it's time to do our analysis, right? So if I wanted to find out the average delay of all flights leaving San Francisco in the month of January 2008, I will run this query. So let's talk about this query. This query is select average arrival delay, or delay at the arriving airport, from my data set, where month is 1, so that's January. My data set is only 2008, so hence it's January 2008. And origin is SFO, so that means, you know, all flights departing SFO. And Hive is going to run this query. So the way Hive runs this query, as you know already, will compile it into a MapReduce job, right? So you notice here that it will list out the starting job. It's going too fast, so I don't want to hold that down. But essentially, I will show you after this job is over. It will list out a URL, which is the MapReduce URL. And that's the job it got compiled to, and that's the job that Hive executed on Hadoop, right? Okay, so that job finished, and the answer is 28.67, right? 669, and that's the average delay of all flights leaving San Francisco in minutes in January 2008. So here's the URL I was talking about, right? So here is the starting job URL. This is the job ID. The tracking URL is this. If you want to go to the web browser and want to see, here I had it open already. If you wanted to see, I'm going to refresh this page. This is the job that got launched, right? So if you can, oh, you probably can't see this, can you? Okay. So this is the regular Hadoop job tracker thing. It's got maps and reduce. So in this case, it launched three mappers, 1 reducer, and all those were fine. So we just ran a Hive query to figure out how many minutes on average was the delay of all flights leaving SFO in January 2008. If you were doing this in MapReduce, right, you would be running a fairly complicated sort of program in terms of just the development cycle to develop that program. And of course, you can use good practices, but I think in general, the overhead of being able to write a SQL query to do what you want to do is just very, very unique. All right, so now we're going to create another table, and this table is going to be called airports table, and I'm going to be sure I copy the entire thing correctly. So this airport table is now get created, and if I do show tables, I will see 2 tables. I will see an airports table, and I will see a flight data table. Flight data table we have already played around with. The table of interest right now is airports table. We just created it. It's empty, and now we need to load data into it, and that is what we're doing here. So I would run this command to load data to the table. It loaded it. If you want to do select star from airports just to verify that everything got loaded correctly, there we go, right? So you see all these airports with their countries, which is US, with their region codes, which appear to be 67 in this case, and the 4th column is their airport code, right? So the reason I have this second data set is because I just wanted to demonstrate a join command, right? And this is our join query. So if you want to join the data set, airports and flight data, nope, okay, I did not copy that right. You would run this query. So let's see what this query does. It's essentially, well, list out the name of the airport and the average delay from that airport for flights from flights originating from that airport in the month of January, and you group by their name, right? So if I wanted to figure out the flight delays for all the airports, this is the query I would use. And let's say I could have done this with just one data set, which have been in the fact data set, which is the flight data data set, but I would have only gotten airport codes. If I wanted to get airport names, I have to join it to another data set, which is airports data set. I joined it with that, and I would get what I expect. So the query is running. It's still running. It launched a MapReduce job, and it's running in the background. So once that finishes, we'll see some data. So notice in this case, it's actually launching 2 queries, right? I'm not sure if it's very clear to you guys, but the first query, the first MapReduce jobs ID was 002 in the end, and this one, the one that just launched right now, is 003 in the end. So in this particular case, Hive launched 2 MapReduce jobs to do what it wanted to do. Okay, so here's our result. You can see, I don't know, pick an airport and you will find the delay. Anyways, I will let you do that exercise at home. I am almost done with my presentation. I do want to talk about just 2 more things and we should be done here. Applications of Hive, web analytics is one of my favorite, retailers, healthcare, genome sequences, I've talked about all of that. Spam detection, data mining, optimization of advertisements, and ETL workloads. I really wanted to talk about this slide. So if you have been wanting to try out Hive and you don't really know how to get started, right? This is a good slide. So you can obviously get started with Hive using the tarball that's available on the Apache Hive website. Keep in mind that Hadoop is a dependency, so you will need to install Hadoop and configure Hive to use that Hadoop. There is an open source project called Apache BigTop, which I also work on, which will give you packages, Debian and RPM packages, and will manage your dependencies. So if you add the BigTop repository, you can just do sudo apt-get install Hive, and it will install Hadoop for you, and it will install Hive for you, and it makes your life a lot easier in terms of installation and deployment. And obviously, the packages are available for Debian and for RHEL and Fedora, a whole bunch of other operating systems. So if you have a Linux operating system of your choice, please go try out BigTop. The third is what I did in this presentation. I used a demo VM. So Cloudera has a demo VM, for example, that comes everything pre-installed and configured, right? All you do is boot up this demo VM and play around with it. So if you have a Windows box or you're just too lazy like me, just pick up a demo VM, download it from some site. Cloudera, as I said before, has a demo VM, and off you go, right? Start typing Hive commands and expect them to work. If you want to learn a little bit more about Hive, there's this Programming Hive book that's written by a lot of good people, in particular Edward Capriolo, who's also based in New York City, is one of the authors of the book, and definitely a recommended read. And if you have any more questions, that's my Twitter, that's my GitHub, that's my LinkedIn, and that's my email. Anyways, so I'm going to ask Mehul to take any questions that you guys might have. And of course, if you don't get a chance to ask questions that you wanted to ask today, feel free to reach out to me and ask them online.
So Mark, can you hear me?
Yes, it's a little muffled, but I can mostly hear what you're saying.
I'm trying to see if I can pass the mic around so we can ask the question. So we can do that as well.
Okay. No, this is fine. If I can't understand, I'll ask for clarification.
Did you talk about the relative merits of Hive versus Impala?
Okay, so if I understood that correctly, sorry, did I cut you off?
That's a question.
Okay. Okay. So the question was about explaining the difference between Hive and Impala. So Impala, for those who don't know, is another SQL query engine that runs on top of Hadoop. It's a part of the ecosystem. In general, its performance is better than Hive, but I still think there are very different use cases for both of those systems. They are similar because they both allow people to write SQL-like queries and mine their data that way. The reason they are different is mainly because of the pluggability aspect. So Hive has a very pluggability-oriented model where you can write your own, format your own UDF, your own survey, your own aggregate functions, while Impala is not at that stage yet. Impala, at the moment, as far as I know, doesn't have certain features that are present in Hive. For example, windowing functions, which are functions that you can provide a window of and say, I want the first from this window or the last from this window, are not available in Impala. So at the end of the day, I think it depends on your use case which product you should go with. They're complementary. They are both similar because they are SQL-like engines. At the same time, Hive is more geared towards pluggability. There are certain features that may not be there in Impala right now, and Impala is a faster query engine written in C, but doesn't have as much of pluggability at the moment as Hive.
Thank you. My question is related to Hive and Pig. If we have a UDF which I have written in Hive, can I directly use it in Pig, or is there a connector?
Right. Okay. So the question was, given that there are two projects, Hive and Pig, and I have written a UDF in Hive, can I directly use it in Pig? I actually do not know the answer to that question. I haven't played around with Pig all that much to be able to answer that question. Pig does have a concept of UDFs. They are also written in Java. How similar or different they are from Hive UDFs, I wouldn't be able to say. There are a bunch of Pig UDF libraries like DataFoo that exist around there. DataFoo is a library from LinkedIn, and it integrates well with Pig UDFs. I'm not sure if Hive UDFs will be directly accessible to Pig for use.
No issue. I have one more question. Can you talk a bit about security in Hive?
Security in Hive. Okay, so good question. When people talk about security, there are two things they refer to. They refer to something called authorization, and they refer to something called authentication. All right. So, and what these two things are, the first one is where you want to allow or disallow a particular person from logging in, right? I want to be able to allow Mehul from logging into Hive and accessing the Hive data warehouse, but not allow, somebody else, myself, to be able to do that. I don't know why I would do that, but that's the use case. And that can be easily achieved today in Hive using Kerberos and Sassel. It essentially plugs into your existing Active Directory or LDAP sort of authentication framework and authenticates your users through that from being able to access Hive or not. So that exists, and it's usable, and encourage you to use it if that's important to you. The second part is limiting access to users who are logged in to certain parts of your data. So limiting people to allow or disallow them creating tables in a particular schema, or maybe let them see all columns of the table but the one that contains the social security number and the credit card number. So stuff like that. That requires a little bit more work in Hive. There are different ways you can implement that. There's fine-grained locking and coarse-grained locking. And the way it has been implemented in Hive today doesn't work for all use cases. There is work going on in the community to change that, to have better access control. And so hopefully that will come out and be out in the community sooner than later. But authorization works using Kerberos and Sassel. And access control is there. It may not solve all use cases, but it's a work in progress.
Thank you for your talk, Mark. My question is about Metastore. So, correct me if I'm wrong, but it's like the DDL is stored in Metastore, all the information on all of the mapping of your schema that it to help facilitate the translation of HTML into the data representation. Question is, how resilient is to dirty data? For example, let's say you're loading data and your data doesn't directly map, or some of the data in your set don't directly map. It's going to crash a query, is that row, what can I expect? For example, I'm loading JSON, present, all of the JSON objects I'm loading into the system. Maybe you can talk about that a little bit.
All right. I'm going to have to apologize to you, sir. The only thing I understood from that one was that you have a question about the Hive Metastore, and it was something to do with the mapping of data types to the Metastore. But apart from that, it was all very muffled. I'm sorry. So you may have to just repeat that. It was a little choppy.
I'm sorry about that. The question is about how resilient the system is to dirty data. If you're loading data that's, let's say, a JSON object and some keys aren't present, and the EDL is calling for those keys to be present, and you're using it in a query and it's not available, does the system skip rows? Does it stop the query? What happens in those cases?
Okay. I missed that. Hey, Mehul, I think you may have to either type that question to me while someone else asks another question. I'm sorry, sir. I'm going to get back to you once I have a better handle on the question.
So, Mark, let me try to rephrase the question. Question, I think,
okay.
is what if the underlying actual raw data does not match the schema you have defined?
Oh, I see. So if that happens, if you noticed in my demo, I was always doing a select star after I loaded up the data, right? So that is my way of validating that the schema that I created that got persisted in Metastore is valid, right? So the question was, what happens when the Metastore schema that you persisted does not match with the actual data on HDFS? So if that is not the case, you will see nulls in your data, right? And I will go ahead and answer the question that may have been asked, and I'm sorry again for not being able to pick that up. Your schema is subject to change, right? So today you have 10 columns in your data, and tomorrow you may add another 11th column. And how would you make sure that Hive will handle that properly? And the answer to that question is it will if your schema changes in a backwards compatible way, right? So if you added a column at the very end of the file, all you do is you run an alter table command, and you add a column at the end. For data that doesn't have the column in the end, you would see nulls. For data you have that column in the end, you will obviously see the correct value of that column. For other things in which you use fancy surveys that you created on your own, you will just try to make sure that that's case, define backwards compatibility for your own survey and make sure that compatibility is met as the schema evolves. Does that answer the entirety of the question?
Thank you.
Thank you.
Yeah, I have a question. Could you explain the interaction between Hive and Avro?
The difference between Hive and Avro?
The interaction. How do they interact?
Oh, the interaction between Hive and Avro. Okay, so the question was, can I explain the interaction between Hive and Avro? So Avro is a format, just like sequence file, just like text file, or any other format. Hive will use surveys to serialize or deserialize any format. So in my examples, I had CSV files. These are called text files in Hive terminology. And Hive has this built-in survey which will read that file, serialize it, read that file, deserialize it into a set of records, and do vice versa. In Hive, there is something called the Avro survey, right? And that's what that survey does as well. it will take a file that's in Avro and it will deserialize it into a set of columns that people can read from as a table. And there's a serialization part, of course, which will do the reverse. So Hive has built-in support for Avro, just like it has built-in support for other file formats. That said, if there's a format that you want support for, come add a Serde, or if it's some proprietary format that you use, deploy Hive and write your own Serde and put that in your Hive queries. Essentially, in your Hive create table statements, you refer to the Serde you want to use, and be able to munge on your own custom format.
Thank you.
Sure.
Hi. Thanks a lot for a very informative presentation. I have a question regarding the load operation. Does the load data into the table operation leverage MapReduce? And the next part is, if let's say I have 4 to 500 million rows of roughly, let's say 50 GB data size, how much time is a moderately complex schema, which I want to represent in Hive, roughly how much time it will take in your experience, or maybe extrapolate?
Right, okay. So great questions. I will talk about them one by one, except that I can't remember the first question you asked.
Does data load operation leverage MapReduce behind the scenes?
Right, okay, so the first question is, when I did the load data command, did that actually launch a MapReduce job, right? And the answer is no. A load data command transforms to an HDFS put command. An HDFS put command, in general, doesn't require a MapReduce job. Now, if you were inserting data into Hive from another Hive query, you're obviously running a MapReduce job or a map-only job that will write the data into the destination. But in my particular example, it was a simple Hadoop put command, or equivalent to a Hadoop put command, and that is why it did not launch a MapReduce job. The second question, and please feel free to correct me if I got that wrong, was that if I have massive amounts of data that I want to transfer to Hive and use it that way, how many load commands do I need to run? How would that work? Is that correct, sir?
Yeah. How much time approximately typically would take, let's say, MapReduce, let's say, 500 million rows?
Right. Right. So it's very hard for me to say anything time related because it depends on the number of nodes in your cluster, how you're going to distribute this data. But I would say is that Hive is built on top of Hadoop. And in this particular case, the part of Hadoop we are talking about is HDFS, right? Because we're talking about throwing files onto disk. When you get to stage where you want to dump a bunch of data onto HDFS on a periodic basis, usually that's what people do, you should consider using other parts of the ecosystem. So there's this project called Apache Flume, which will essentially transfer data from, let's say, your web server or a log4j file to HDFS, and you can create a table on top of this data without having to do any copy, right? So Flume does all the nasty, dirty work of taking data from your source and putting it into the sink, which in this case is HDFS. And Flume supports a whole bunch of sources and sinks. The most common one is obviously log4j, but there are a whole bunch of other sources. Sinks, obviously there are many of them. You have a HDFS sink that you can just use to create a table on that. If you do that, Hive doesn't need to do any load data command. All you do is when you create that table, you specify the location of your data set, which already exists in HDFS. Another example is that you may have some data that exists in your relational database that you want to bring over to Hadoop. And there is another Apache project that will let you help with that, and that's called Scoop. Scoop stands for SQL to Hadoop, and it allows you to transfer data from your relational SQL database to Hadoop, and also export data from Hadoop out to your relational database. So when you get to that point, I will strongly recommend considering one of those projects depending on your use case, because I don't think Hive is meant for transfers of data. Like that, I use those commands in this case, but that was a demo purpose. If you find yourself doing that a lot, use Hive for what it is good at, which is data warehousing, and transfer the data using Flume or Scoop.
Okay, thanks a lot.
Sure.
Hey, Mark. Can you use Hive for multi-documents, transactions, or documents to store in HBase? I mean, let's say that you have a block, store the value in HBase. Could you use Hive for multi-document transactions?
Right. So the question was if Hive can be used for documents or various forms of other unstructured data or transactions. So Hive can be used for any sort of data. The only catch there being that you just should be able to deserialize that data the way you want to be able to query that in your Hive queries. So in general, you get all the benefits of storing semi-structured and unstructured data in Hadoop via Hive, right? You don't lose any of those benefits. Whatever you can do in Hadoop, Hive will be able to expose that to you as long as you write the serialization and deserialization library the way you want it to be. As far as the last part of that question goes, transactions, I'm misunderstanding it, or if that's the case, please correct me. Like I said before, the transactions are not supported. Like HBase will support transactions, or any other relational database will support transactions. Hive will not. It's more like an OLAP server database data warehouse instead of an OLTP warehouse.
Could you talk about the join performance of Hive, guys going together to leave a table on time, and part two, that's
yeah, I'm sorry. Someone will have to repeat that question. Mehul, could you repeat that question for me, please?
Sure. Can you hear me now?
Yeah, actually, that was much better.
Okay. Could you talk about the join performance of Hive? If I want to join together a million row tables, and I do that in a reasonable amount of time. And part two, you can contrast that to writing that to cascading or something like that to join.
Okay. I'm going to repeat that question, and please correct me if I got it wrong. You want me to compare the performance of Hive versus writing a MapReduce job for doing the same thing?
Yeah, specifically to join, if I want to join very large tables.
Oh, I see. Okay. Yeah, great question. So the question is, how does Hive's performance compare to a MapReduce job's performance, especially when, say, you're doing joins? I would go as far as saying that Hive's performance is pretty comparable to what you would get by writing a MapReduce job for doing the same thing. However, if there is certain thing you know about the data that you can make use of in your MapReduce job that Hive cannot make use of because you never provided that information, or it doesn't have that feature to make use of that information, then your MapReduce job is obviously going to be faster. So in general, if the methodology of join that you're using in the MapReduce job is comparable to the methodology of Hive join, then you're going to be fine. And Hive has various different join methodologies which work in certain cases. But let's say if your data was present in 3 different files, and you knew that so if you were joining two tables and the data was present in 3 different files in each of those tables, and you knew that the record that appears in file 1 of table 1 can only appear, the corresponding record can only appear in file 1 of table 2, and so on and so forth, then essentially you will only be joining file 1 to file 1, file 2 to file 2, file 3 to file 3, right? If you do just a simple regular join in Hive, Hive is going to join the entire table 1 with table 2, and because it's an n-squared operation, that's going to be much slower because Hive didn't know about these 3 files and the added knowledge that file 1 records can only be present in the file 1 of the other table, right? So the way to get around in Hive is, in this particular use case, it's called a bucketed join, where you have 3 files. Each of these files is called a bucket. So we call it, you have 3 buckets, and you can do a bucketed join in Hive, in which case Hive knows that the user has supplied me this particular information saying that only corresponding buckets need to be joined. And in that case, the performance would match up, right? So in general, the performance matches up as long as there isn't some information about the data that you are hiding or that Hive can't make use of.
Let's say we have data at Hive. Now, all of this dashboard system in Tableau or some machine learning, would they be able to tap into the Hive database? Are they
I'm sorry, could you repeat that question again?
So Mark, my question is, are there APIs into Hive for other third-party vendors to be able to leverage the data in Hive? For instance, let's say I'm using Tableau for reporting and dashboarding, or
Right.
I want to use some machine learning tools, and I write some algorithm.
Right.
Would I be able to
Right.
access?
Right. That's a great question. The question is, if I'm building some sort of app or connecting another app on top of Hive, what kind of tools and integration exist for me? And so the best answer that I can give you at this point is the Hive exposes a JDBC interface, right? So a lot of tools like Tableau will make use of that interface and integrate with Hive that way. I have definitely written applications in the past where I have just used Hive's JDBC application and JDBC client to be able to connect to Hive and write queries. In that respect, it's very similar to any other database that you might have been using. So I think the level of integration available right now is through JDBC and ODBC drivers, and given my personal experience, I've been very satisfied with that.
Any other questions?
So Mark, I think that wraps up the questions from our side. Appreciate the time you gave us. And
absolutely. Well, thank you everyone for coming. I'm sorry I had a little hard time understanding your questions, and if I missed any questions or if you had any more questions, please feel free to reach out to me. And thanks again for taking the time to talk to me.
All right. Thanks again, Mark. Have a good night.
Yeah. Thanks all. Bye.
Yeah, thank you folks for hanging around, and appreciate it coming down. And we hope to see you in the next one. Thank you. Yeah, happy to last time. Yeah. Happy to see more low levels. Happy to use job usually written now.
Java 4 I think they are different, right? Wait, like from
And happy to use what?
it's just one just press name and
If you are accessing Hadoop, you have an HDFS. So you write batch jobs that will go to the server and process the data for your query. And the reduce, what it will do is it will combine the data from